Welcome back to the Mechanics of Solids lecture series. We're looking at examples calculating bending stress and bending moment of inertia in beams. The next one is a comprehensive example. We're asked to compute the peak normal stress in the beam due to the applied loading and indicate where it occurs. The section is a rectangular tube section, and the beam itself is a simply supported beam with a series of point loads. In order to find the peak normal stress, we need to find the maximum bending moment in the beam, so we're going to need to draw a shear force and bending moment diagram. Then we'll need to calculate the moment of inertia of the cross section, and finally calculate the stresses using a y value equal to half the distance of the section to calculate the stress at the top and bottom of the flanges. So we'll start with our shear and bending moment diagram. First, note that the beam itself, we develop reactions A sub y at support A and B sub y at support B. Because of the symmetry of the loading, the reactions are going to be equal. The total load is 40 times 3 or 120 newtons, so we have a reaction of 60 newtons at each support. Now I'll extend the lines down in order to draw my shear force and bending moment diagram. I have lines extended from each point of application of a load. I'll make an axis for the shear force diagram, V in kilonewtons, and an axis for the bending moment diagram, V should be in newtons, M in Newton meters. Starting with the shear force diagram, shear jumps up by 60 newtons. We reach the first load, it jumps down by 40 newtons to 20, jumps down another 40 to negative 20, and it jumps down another 40 to negative 60, and at point B it jumps back up 60 and comes back to 0. Now for the moment diagram, starting from the left end, the moment is 0, the moment increases linearly, and the value at the first line or intersection is 60 times 3 or 180. Then it continues to increase but at a lower slope, which I'll draw like that. The value in the middle is 180 plus 20 times 3 or 240. Then it's going to decrease by the same amount back to the third point, which comes back to 180. Sorry, that should be 180. And then decreases again back to 0. And I can tell that it's going to decrease the same way that it increases because of the anti-symmetry of the shear diagram. Now to calculate the moment of inertia. I can calculate the moment of inertia of this section as I of the outer rectangle, using the outer dimension, as if it's a solid section, minus I of the inner, which is the hollow part. So I'm subtracting away the part of the section that is inflated. Using BH cubed over 12 for each rectangle, I of the outer is 40 times 26 cubed over 12. Notice I'm taking I about the z-axis. I take the dimension in the z direction as b. I take the dimension in the perpendicular direction as h, and that's what I cubed. Minus I inner. The inner dimension is 40 minus 3, 1.5 for each wall, which is 37. And the inner height is 26 minus 3, or 23 cubed over 12. This computes to 21,072 millimeters to the fourth. Now for the stress, sigma max equals, using my over I, but taking c, the value from the neutral axis to the top or the bottom of the section, mc over I, where c top and c bottom are both the same and equal to 13 millimeters, or half the height. I'll just compute the value. Notice I've dropped the sign. I'll just compute the value and then reason the sign by inspection. So the moment, the maximum moment in the center of the beam, 240 Newton meters. I'll convert that to 240,000 Newton millimeters, because I want my units in newtons and millimeters, times C, 13 millimeters, divided by I, 21,072 millimeters to the fourth. That gives me resulting units of newtons per millimeter squared, or megapascal, which is what I'm looking for stress. And this computes to 148 megapascals. So that's the value of the maximum stress. The other part of the question asks us where it occurs. We know it occurs at the center or midpoint of the beam, because that's where the maximum moment is. And we also know that it occurs at the top and the bottom of the section. And because of the symmetry, the stress is equal and opposite at the top and the bottom. For positive internal moment, bending smiley face in the upward direction, the top is in compression and the bottom is in tension. And that concludes this example.